Hey everybody. So last time we introduced the Schrodinger equation and how to solve it for this infinite square well potential. And so this time we're going to discuss how to use this wave function, and any wave function really, to figure things out about our system. So the first thing that you can use the wave function to figure out, though, is the probability. So you might remember that the probability density is the absolute value of our wave function squared times dy or dx, depending on the dimension. And then if you want to know the probability for something, first you have to normalize your wave function. And so that involves taking the integral over all space of the absolute value of your wave function squared, or that probability density. So what I'm going to do now is show you how to normalize the particle in a box, the infinite square well. So remember, we said last time that our wave function psi for the particle in a box was the amplitude a times the sine of n pi x over L if the box runs from 0 to L. And then our wave number is 2 pi over lambda, which is equal to n pi over L. We solved for that last time. So psi squared would be the absolute value of a squared times sine squared n pi x over L. And then when we stick that into our normalization condition, we're going to integrate that from minus infinity to infinity, and then force that to equal 1. Remember, the normalization condition is that the probability of the particle is somewhere is 100% or 1. Now, what you've got to do if you're integrating over all space, there's basically 3 regions. There's the regions where the wave function is 0, and the wave function is 0 for x less than 0 and for x greater than L. So you see here that I've set up 3 different integrals here. I'm integrating from minus infinity to 0, my wave function is 0 there, and then I'm integrating from 0 to L, and then I've got a squared sine squared dx, so that's what I'm integrating there, and then from L to infinity my wave function is 0 again. Now in later integrals that we're going to do where we have to integrate over all space, I might just drop the part for less than 0 and greater than L because the wave function's 0 there anyway. But please understand that it does appear, okay? It does appear, it's just 0. So the only part that's non-zero then is 1 is equal to, now a is a constant, so you can pull that absolute value of a squared outside of your integral and then integrate from 0 to L of the sine squared n pi x over L dx. All right? So to do that integral, I'm going to use the trig identity. And a trig identity that is useful for this one is that the sine squared of an angle is equal to 1/2 minus 1/2 the cosine of 2 times that angle. So plugging that in, my angle here, theta, to plug into this identity would be n pi x over L. So I'm plugging that in, and then I end up with 1 is equal to the absolute value of a squared times the integral from 0 to L of 1/2 minus 1/2 cosine 2 n pi x over L, and then I'm integrating all that with respect to x. All right. So the integral of 1/2 with respect to x is just 1/2 x, and then I'm going to evaluate that from 0 to L. And the integral of 1/2 cosine 2 n pi x over L, the integral of cosine is the sine. And so then you end up with minus 1/2 L over 2 n pi sine 2 n pi x over L, and then you evaluate that from 0 to L. All right? Now, if you're evaluating the sine bit, the sine 2 n pi x over L, you're subbing in for x at x equal to L and x equal to 0. And so what you end up with at your endpoints is the sine of 2 n pi and the sine of 0. And both of those things are 0. Okay? So this second term in your integral, that goes away. It's 0. And then you just end up with 1 is equal to the absolute value of a squared, and then times 1/2 L minus 0, which is just 1/2 L. And so then when you solve for a squared is equal to 2 over L, and then that means that a is equal to plus or minus the square root of 2 over L. Okay, so we've now fully solved for our wave function. So we can use it to find the probability for a particle to be in that infinite square well in any position. Now, to remind you, in general, when you want to find the probability that a particle is between A and B, you just integrate that probability density psi squared dx between A and B. Okay. So let me show you how to do that for the infinite square well. So the example that I'm working here is, what's the probability that a ground state particle is between 0 and L over 2? In other words, what's the probability that that ground state particle is in the left-hand side of the well? All right. Well, if somebody asked you, you might just say 1/2, right? Because it's just as likely to be on the left as the right. And you'd be right. But here's how to do that mathematically. All right. So we're going to integrate our probability function from 0 to L over 2. Our probability function we now know fully is root 2 over L sine pi x over L. Remember, n is equal to 1 for the ground state. And then you square that and then integrate it with respect to x. So our integral looks like 0 to L over 2, 2 over L sine squared pi x over L dx. We're going to use that same trig identity that we used last time to solve. So we're going to plug in for the sine squared and make it the 1/2 minus 1/2 cosine of 2 times the angle. We're going to use that same identity. So plugging in that identity into my integral, I get probability is equal to 2 over L, integral from 0 to L over 2, 1/2 minus 1/2 times the cosine of 2 pi x over L, and then integrate that with respect to x. When I do that, I get 2 over L, 1/2 x, evaluated from 0 to L over 2, and then minus 1/2 L over 2 sine 2 pi x over L, integrated from L over 2. Okay? When you evaluate that integral at the endpoints, you, yet again, your sine term, that second term, that's going to go to 0 because you've got sine of 2 pi over L times L over 2, and then that gives you the sine of pi. All right, and sine of pi is 0, and then of course the sine of 0 is 0. So that part, the sine term, that goes away. And then you're just left with 2 over L times 1/2 times L over 2, and you get 1/2. Okay, so it's just like you expected. Now, you might have to do more difficult integrals to get probabilities in different regions, but basically, you know, the math is going to give you the same value. I mean, the math is the same. It's just a crank that you turn. Okay, so here's what the probability density function looks like for that particle in a box. We went over this last time, but I'm going to remind you. It's just that sine squared function, okay? Now, you can see here that the probability function is maximized at some places and it's 0 at some places, okay? So the probability is, it varies over the well. Now, Bohr's correspondence principle, that says that in the limits where classical and quantum theories should agree, the quantum theory must reduce to the classical result. In other words, quantum mechanics is a more encompassing theory than classical. And so if quantum doesn't give you the same answer as classical, then something's gone wrong, right? So here's how that would apply to the infinite square well for these probabilities. For a classical particle, the probability of finding it in some space dx is equal to the fraction of the time that it spends in that space, right? So if you have some classical particle now, not a quantum particle, but a classical particle, bouncing back and forth, okay, in between the walls of your infinite square well, then what you'd have to do is, for a certain slice, figure out how long it stayed in the slice compared to its total time. Right, so let's just say that the time that it takes the particle to hit one wall, go hit the other wall, and bounce back, we'll call that the period of the motion, kind of like a spring moving back and forth, all right? So that's the period. We'll call that capital T. Then the probability classically that the particle is in this region dx, okay, is that amount of time that it spends in dx, which I'll call dt, little t. And then we'll divide that by t over 2. Okay, why t over 2? Because it's going from left to right, okay? And so that's half the period, but it should tell you for one trip, all right, 1/2 the trip, I guess I should say, going from left to right, how long it's going to spend in there, okay? So then if you figure out what the speed of the particle is, let's just say that you have a general function for the speed. Remember that the speed is equal to dx dt. So rearranging that, then dt would be dx over v. Here I say v is a function of x in case the speed varies as it travels through the well. So dt is equal to dx over v, and then we divide that by the period over 2. And that would be your classical probability. How long did it spend in there? What fraction of the time? So classically, your probability would be 2 over the period times the speed, all right? What this means, if you want to interpret that, is that a particle is more likely to be found where it's moving slowly and less likely to be found where it's moving quickly. That just makes sense, right? Okay, so the classical particle in the box, what happens is it's got a constant velocity between the elastic wall collisions. It's just going back and forth, okay? And so we'll call that constant velocity between the walls V naught, just something, okay? So that means that the probability classically that it would be in a slice at a position X would be 2 over T times V naught, okay? Now, what would be the period there? The period would be the total distance that it travels divided by the period would give you the speed. So that means that V naught would be 2L, okay, over T. All right, so then if you plug in what T would be, it would be 2L over V naught. So you're plugging in for that here, okay? And then you're multiplying that period times the speed V naught, and the V naughts cancel. And then you would get that the probability, classically, that the particle would be at any given position X would be 1 over L, where L is the length of the box. What that would mean is that as long as the velocity is the same everywhere, the probability is the same everywhere, right? That makes sense if you think about our argument that we said earlier. The particle is more likely to be found in places where it's moving slower. Well, if it's moving the same speed all the time, then the probability that it's in one particular location shouldn't be any different, right, from location to location. All right, now, if you look at what the probabilities are for the particle in a box, a quantum particle now, then it looks like that sine squared function. Now, you can see here on the left in this image, there's the plot of what that looks like for the ground state. It's just kind of that one hump there. And you can see that that's really not a very good match for the n equal to 1 state. Those two functions really don't look alike at all. But you can see that as you go up in energy, okay, as you go up in energy level, and now you're at a really super high energy level. On the right, it shows n equal to 20. Then what that would look like is a really screwy little sine function, right? Little sine squared function. Now, the amplitude of that would be 2 over L, because remember, it's psi squared, and so you'd have 2 over L times the sine squared of n pi x over L. Okay, so the amplitude, the total height from peak to peak of that function is 2 over L. And then it wiggles around. So if you take the average of the wiggle, okay, then that would put you dead in the middle of 2 over L, which is 1 over L. So as you go up in energy level, the average value of where the particle is located is the same everywhere, and it's 1 over L. Okay, so as you go to higher and higher and higher energy level, you'll get more and more squiggles, and you'll more closely match the classical prediction. So that's kind of Bohr's correspondence principle as it applies to a probability for a particle in a box. As you grow your box, okay, as you get closer and closer to a classical limit, then it starts to look more and more classical. Okay, so what else can our wave functions tell us? We can figure out the probabilities, and we can also figure out the expectation values. What's an expectation value? Well, an expectation value is just an average, all right? It's the expected result of the average of many measurements of a given quantity. The notation is, so for example, if you want to find an average, the notation for the average position would be this x with these little triangular brackets around it. That shows you the expectation value of x. Or you could do x and then put a bar over a top, and that's another notation for average value of x. Now, excuse me. Any measurable quantity that we can calculate the expectation value for is called a physical observable. All right, and the expectation values of physical observables, some of the ones that we'll talk about are position, momentum, angular momentum, energy. These are all observables, okay? They have to be real, because if you can measure it, then it must be real. You can't measure imaginary or complex things. So the average value of x, if you calculate it in a discrete way, it's just the number of times that you get value 1 plus the number of times that you get value 2 times value 2, and so on and so forth. So it's the sum of ni times xi divided by the sum of all possible values. You've calculated averages before. Hopefully this is not news to you. Now, what you do is you're going from this discrete case to the continuous case. And that's what we're dealing with when we're dealing with a wave function. So if you go from discrete to continuous, then we're going to use our probability density function, which is our absolute value of our wave function squared, and then multiply that times x and integrate it over all space, minus infinity to infinity. Now, if you took the full analog from the discrete to the continuous, then you would also divide that by the integral of your probability density function from minus infinity to infinity, p of x dx. Now, of course, if your wave function's been normalized, that's just 1, okay? The denominator is just 1, all right? Okay, so what we do is we use our wave function and we stick it in there for our expectation value. So we have the integral for the expectation value of x, minus infinity to infinity of x times psi star psi dx, and then we integrate that. And then, of course, yet again, our denominator for a normalized wave function should be 1. Now, we can do this for other physical observables as well, and I'm just going to call the expectation value for any function, g of x, whatever our observable might be. We'll talk about more later, but there's going to be functions that describe those observables, and I'm just going to call them generally g of x, okay? And so then if you have some generic, g for generic, observable, then the expectation value of that observable is the integral from minus infinity to infinity of psi star, remember psi star is your complex conjugate of your wave function, psi star g of x psi dx. So you're just performing these integrals, all right? An example is priceless here. So let me calculate the expectation value of x for a particle in a box, okay? So the expectation value of x would be the integral over all space of psi star times x times psi dx, all right? Now, you may see here that I've only written the integral from 0 to L. So remember that for the particle in a box for an infinite square well, the wave function is 0 everywhere else. So there are some terms here that are understood to be 0, the integral from minus infinity to 0, and the integral from L to infinity. That just gives you a 0 term, okay? So I'm going to integrate then. The 0 parts go to 0, so I don't have to integrate them. And then I'm integrating 0 to L, 2 over L, sine squared n pi x over L. And then I'm multiplying that times x, okay, and integrating with respect to x. And this is how we calculate our expectation value, our average value of x, for the particle in the square well. Now note here, for our particle in a box, our wave function is real. Wave functions can be complex, but they don't have to be complex, okay? And for our particle in an infinite square well, psi star is equal to psi because our wave function's real here. Okay, now, you're integrating x times sine squared of some stuff times x, okay? I use integral tables here. You can use integral tables too. I'm really not concerned so much about whether or not you can do the calculus. So if you want to buy a math handbook, I use my, you can tell it's a very old math handbook by Shams. I use this thing all the time, and I look up integrals because Calc 2 is over. So here, from the tables, the integral of x times sine squared of ax dx is given as this x squared over 4 minus x sine 2ax over 4a minus cosine of 2ax over 8a squared. Okay, so this is what appears in the tables, and my integral, actually, here a is equal to n pi over L. Okay, so I've identified here, and my a value is n pi over L. And then I'm just plugging and chugging what my integral is into this value that I got out of the table. So if I do that, then my expectation value of x is equal to 2 over L, x squared over 4, minus x sine 2n pi x over L over 4n pi over L, minus cosine of 2n pi x over L over 8 times n pi over L squared, okay? And then I evaluate that from 0 to L. When I do that, I get 2 over L, and then first evaluating at L, I get L squared over 4 minus L over sine 2n pi over 4n pi over L minus cosine 2n pi over 8 n pi over L squared. And then at the 0 term, I get 0 for the first two terms, and then minus cosine of 0 over 8 n pi over L squared, okay? So when I figure all this stuff out, I get 2 over L, L squared over 4. The the sine of 2n pi, that goes to 0. And then I have the minus cosine 2n pi, that goes to 1. Okay, so I have L squared over 4 minus 1 over 8 n pi over L squared. That sine term goes away. Okay, and then in the second bit, the cosine of 0 is 1, and then I have plus 1 8 n pi over L squared. So you might need to stare at that a minute just to make sure that you understand where everything went. But some things went to 0 and some things went to 1. Now I have minus 1 8 n pi over L squared and plus, and so that cancels out, and I'm just left with the L squared over 4 term, and then I have 2 over L squared over 4, and that's equal to L over 2. So somewhat unsurprisingly, okay, after all that math, I end up with the totally unsurprising result that the average position of the particle in a square well is in the middle. Okay, woohoo, way to go me, right? Totally unsurprising. Okay. I'd like to point out, though, that the average isn't the same as the probabilities. It turns out that the average position for the particle in the square well is, always in the middle. Always in the middle. You see here, I did that integration for a generic value of n. Okay, so the average value is always in the middle. But if you look at what the probability density function tells you here, let's look at this n equal to 2 value. For n equal to 2, the probability that the particle is in the middle is 0, okay? And the probability is maximized here at L over 4 and at 3 L over 4, all right? But the average of those two numbers is still L over 2. So you see the idea of a probability that it's actually there and an average value. Those are two different ideas. I hope that's clear. Okay, so we've talked about position. Now let's talk about how to calculate the momentum, the average value of the momentum. To do that, we need to first define the momentum operator, okay? There are operators in quantum mechanics. So what we're going to do is to find the expectation value of our momentum p, we first need to represent p in terms of the position and the time. All right? So if you look at what a generic wave function is, let's just define our generic wave function, time dependent, as e to the ikx minus omega t. So that's our generic wave function. Let's take the partial of that with respect to x and figure out what we've got there. So if we take the derivative of that with respect to x, then we get ik, right, times e to the ikx minus omega t. So basically we get ik times our wave function again. We get that back. Now remember that k is equal to p over h bar. We talked about that a bunch of times. So what we're saying is that if we take the partial derivative of our wave function psi with respect to x, that we get I times p over h bar back times our wave function. So now we can solve. We can solve for p times our wave function. And p times our wave function would give us minus ih bar times the partial of our wave function with respect to x. So if we want to know what p is, we just take that partial with respect to x and multiply it times some constants. And that's our momentum operator. So our momentum operator is minus ih bar times the partial with respect to x. If we work that operator on our wave function, we'll get our momentum back. Okay? So it's the momentum operator. Okay? I know it's kind of strange, but this is an idea that actually comes from classical mechanics. So if you go on and you take the 3000 level classical mechanics, physics 3010, then you'll deal with operators in that as well, okay? And it comes from Hamiltonian physics. So Google it and you can see what I'm talking about there. All right, so we're going to say that the expectation value of the momentum can be found by operating our momentum operator on our wave function. So that's going to look like this, minus ih bar times the integral from minus infinity to infinity of our complex conjugate of our wave function times the partial of the wave function with respect to x dx. Okay, so we've worked our momentum operator on that second wave function. What you do is you stick your operator in the middle of your psi star psi. So you have psi star operator psi, all right? Or I guess from your perspective, psi star operator psi. I don't know. backwards, forwards. But anyway, you stick it right there in the middle. So that's what we've done there for that expectation value of the momentum. So the expectation value of any operator, what you can do is stick it in the middle, okay? So you have the expectation value of some function or operator f of x, and you stick it there in the middle, minus infinity to infinity, psi star f of x, psi dx, all right? And that's how you calculate an expectation value for any generic operator. You put it in the middle of the wave function and the complex conjugate, and you integrate over all space. Now, if you have a wave function like our position wave function that we did back, that's just simply some function of x, like x or x squared or whatever, then it will commute. In other words, the order doesn't matter. You could do psi star psi times x, or x psi star psi, and the order doesn't matter, okay? But operators like momentum that contain derivatives, that doesn't commute. So you can't put a derivative anywhere you want. You have to put it on a specific spot, right? And that's why it's really important for operators like momentum that you put it in the middle so that when you operate it on your wave function, you get your momentum out, all right? So make sure that you understand why that's the case. Some operators commute, some operators do not commute, okay? So for example, in case you're wondering what the heck I mean when I say commute, certain operations commute. A plus B equals B plus A. But division does not commute. A minus B, or A divided by B doesn't equal B divided by A. And certainly taking a derivative doesn't commute, right? So it's very important that you put it in the right order. Also, I'm talking about partial derivatives. Okay, so in case you've forgotten or have totally gone away, a partial derivative is represented with little curly d's. So it looks like these little curly d over curly dx. Okay, so that's a partial derivative. And what you're doing there is you're taking the derivative only with respect to x. Okay, partial derivatives are actually easier to take than full derivatives because you're ignoring any implicit dependence on time or on some other variable. Okay, so it's not the same as taking a full derivative, it's easier. So when you take the partial derivative with respect to x, then you have to multiply times dx dt or whatever when you're done, right? But in a partial derivative, you're ignoring any other variables and you're treating them like a constant. So for example, if I have a function like xyz that's a function of 3 variables, and I'm taking the partial derivative with respect to x of those 3 variables, right, then I can just treat y and z like a constant. And the partial with respect to x of xyz would just be yz because you're only taking the derivative with respect to x. So partial derivatives are easy. Okay. So now that I've said all of that, let's go ahead and figure out what our average value of our momentum is for the infinite square well. Okay? So what I've done here is I'm plugging in my momentum operator here in the middle. And my momentum operator is that minus I h bar over I, same diff, partial with respect to x. Okay? So I've got integral psi star h bar over I partial with respect to x times psi dx. Okay? Now, the partial of psi with respect to x for the infinite square well would be the partial with respect to x of the square root of 2 over L times sine n pi x over L. So when I take that partial derivative, I get 2 over L, n pi over L, cosine n pi x over L. So that's my partial psi with respect to x. Okay? Now, when I'm finding my expectation value of my momentum, it's the integral of 0 to L. And now I'm going to multiply times psi star, which is just the same as psi because it's real. Root 2 over L, sine n pi x over L. And then now here is my h bar over I partial psi with respect to x. So here's h bar over I, root 2 over L, n pi over L, cosine n pi x over L. And then I integrate all that with respect to x. I can pull my constants out front, which I've done here. And then I'm integrating 0 to L, sine n pi x over L, cosine n pi x over L dx. Okay? Yet again, let's go to the tables. If you use your integral tables, the integral of sine ax times cosine ax dx is equal to sine squared ax over 2a. And here, my constant a is yet again n pi over L. So using that little handy table value, I get 2 over L, h bar over I, n pi over L, sine squared n pi x over L, over 2 n pi over L, and then I evaluate that from 0 to L, all right? So I get all those constants that I talked about. and then times sine squared of n pi minus sine squared of 0. Well, the sine squared of n pi is 0, and so is the sine squared of 0, 0. So my expectation value for my momentum operator, 0, okay? Now, that might at first seem troubling, because of course it is moving, and it does have momentum. Remember, we already solved what the magnitude of that momentum was, okay? Plugging in for the value of lambda, lambda is equal to h over p. We solved for that in the last lecture. It's nh over 2l. But here's what you remember. Momentum is a vector. It means it's got a direction associated with it. And the average is 0. So all that means is that the particle is going left as often as it's going right. And so basically we should have said that the momentum value is plus or minus nh over 2l, because right would be plus and left would be minus. Okay? So that's our value of our momentum, and because it's going left and right and left and right and left and right, that averages out to 0. Okay? So that's all we're saying. So particles that are bouncing back and forth and spend just as much time going left as going right have an average value momentum of 0. And particles that are confined to an infinite square well potential spend most of their time in the middle, and or their average value is in the middle, and that should also not be surprising. Now, these results seem very simple-minded for the particle in a square well, and that's great. That's why we start with a particle in the infinite square well, because the results make sense. And that leads you to trust the math a little bit more before you start getting into some systems where the results can be incredibly surprising. Okay? So I hope that all makes sense. Don't forget to do the online quiz, and I'll see you when I get back. Thanks. Bye.